We have three graphical models for constant acceleration particle model of motion. We have velocity versus time graphs, position versus time graphs, and we now have an enhanced motion map that can accommodate acceleration. In this video, what we're going to do is enhance our algebraic model so that it can also accommodate constant acceleration particle model of motion. Remember the original data in the position versus time graph that we had for our toy car? When we were learning how to build mathematical models, we saw that a graph that has this shape can be linearized by squaring the horizontal axis values and then replotting that data. Let's try it and see what we can learn. When we square the time axis values, we get 0, 1, 4, 9, 16, 25, and 36 square seconds. When we plot the squared time values against the position, we, not surprisingly, get a nice straight line. If you look at the slope data and build an equation, the equation for this says that position is equal to 2.5 meters for every square second times time squared. If you're observant and have a good memory, you might remember that this is half the value of acceleration that we found earlier. When we were studying velocity versus time, at the beginning of this unit in a previous video, we found that the acceleration for this car rolling down the ramp was 5 meters for every square second. It turns out that this being half of that is not a coincidence. We can explore this by thinking about a kind of a generic velocity versus time graph for an object that speeds up from 0 by some change in velocity over some change in time. The displacement during this time will be the area under the graph. Let's think about what that might be. Here's a rectangle. The width of it is delta t, the change in time. The height of it is the change in velocity during this acceleration. So the area of that rectangle is delta v times delta t. But only half of this rectangle is under the graph. So let's cut the area in half to find out that delta x, the displacement during this acceleration, is the change in velocity over the change in time during the acceleration divided by 2. Now, it might be that we don't know what the change in velocity is. We just know how much time has elapsed and what the acceleration is. So we can use the definition of acceleration to replace delta v in this equation. Acceleration, by its definition, is the change in velocity over the change in time. If we were to multiply both sides by the change in time, we would see that acceleration times change in time is the same thing as delta v. So we can substitute. Where we see delta v in the equation on top here, we could instead put a times delta t because they mean the same thing. When we do that, we get a times delta t over 2 is the displacement. But delta t times delta t is delta t squared, so we can simplify this a bit. And what we find is the displacement is the acceleration times the change in time squared divided by 2. But our car started at 0, and here's what that means. The change in time was just the current time, and the change in position was just the current position. So instead of delta x and delta t in our equation, we could put just x and t. So position for that car rolling down that ramp was acceleration times time squared divided by 2. And if we just regroup a little bit, we could say that acceleration divided by time, or by 2 times time squared is position. And if the acceleration was 5 divided by 2 is 2.5, and that's why that equation showed what it did. Well, not everything starts out from 0 velocity. So here's a more versatile graph where instead of starting at 0, the velocity starts at some starting velocity we're going to call v0. So this would be like a car that's already moving and then it begins to speed up. The displacement, well, it would be the area under this graph. The area under this graph isn't a rectangle like it was for CVPM, and it wasn't a triangle like we saw in our last example. But we can split this trapezoid into a triangle and a rectangle to make our life simpler. We'll consider these two separately. The good news is we already did the triangle. We just finished it. And we know that the displacement is half the acceleration times the time change squared. The other good news is that the bottom part is a rectangle, and that's easy. The height of the rectangle is starting velocity. The width of it is the change in time. And so that's the displacement. So the total area under the graph is the total displacement, and it's just the sum of these two individual displacements. So the total change in position, the total displacement, is the starting velocity times the time change, plus half the acceleration times the time change squared. That equation that we just developed is called the time-dependent kinematics equation. Lots of times it's written in this other more useful way. If we think about what delta x is, it's the change in position. What that is the current position minus the starting position. So we can replace delta x with x minus x0. The right-hand side of this second lower equation is the same as the upper. If we add starting position to both sides, then here's what we get. Now you have a mathematical model that can accommodate not only constant velocity particle model of motion, but also the constant acceleration model